Thank you, everyone. I'm a little unwell today, so I might take a couple of minutes in between the slides. I don't know why I have this little fever-like sensation since morning, but hopefully I won't do a very bad job. So this talk is about running Iceberg end-to-end. If you have it in production or in your POC environment, you're probably already using it, but I just wanted to share a bit of my learnings from the field and how you can build and operate and operationalize Iceberg if you're still evaluating. This is about me. My name is Geetha. I came from California. I live there. I'm actually originally from India. I used to work as a software engineer like 2 decades ago. And then I moved into field-facing sales solutions job at all those companies. And I recently joined Cloudera again a couple of months ago. So Cloudera is going through a lot of transition, and I wanted to speak. This is not a marketing session. I don't want to talk about Cloudera much. Okay, so I worked at all these companies. I recently joined Cloudera again. I was recently at Pure Storage, so I've seen sort of full spectrum of things in the data engineering space. So this talk, I structured it in a way that it'll build on itself. We will start by describing somewhat of a common problem in the data space, and then why I think it's a problem, and then we will go deep into how Iceberg can potentially be a problem solver there, and then we'll get a little into Cloudera's solution of how Iceberg from Cloudera is helping out customers operationalize Iceberg and other multi-analytics engines. And then I have some slides for Cloudera, but if you have any specific questions, you can ask me. So this is basically, I want to start off by saying a lot of data engineers in enterprise world, they build data products and data pipelines, right? When they do build those, they sometimes make a classic mistake of one person running Spark for ETL, and then another data engineer comes and he or she or they put in Trino, for example, for SQL highly interactive queries, and then another person comes in and they'll add Flink for streaming. So what happens is, because they don't necessarily share a table abstraction, common one, they end up having multiple copies of data for each of these engines. And within a year, what you'll see is you'll have 3 copies of the same data set. None of it sometimes will agree. And the bad part is the engineering cost for reconciling all these is sort of high. And I've seen teams, because I'm customer facing, I've seen teams struggle with this 30 to 40% of their sprint capacity time go into data syncing and quality issues, which are purely artifacts of a bad architecture. And what they eventually end up doing is they want to figure out a unified platform or a common table abstraction that where all these multiple engines can talk from. And there is also not just that, there's also inconsistency in results that are very dangerous, because maybe a business facing person like CEO or someone will see data that's different from what a data science team is seeing. It's very important to have same set of data everywhere, and which will avoid trust issues. Iceberg specifically is designed to somewhat eliminate this problem, because Iceberg is basically a specification, right? Not necessarily a library. It's a specification designed at that layer and not at the API layer. So it will, it's not like a wrap around Hive, or if you're aware of if you go back to the initial days, Hive Metastore, how many of you know Hive? Yeah, thank you. It's pretty old, but it's still intact. When Hive Metastore was designed, it was a major step forward back in 2010 towards cataloging things and having metadata store. But that was built around Hadoop's assumptions that you have strict partitioning or directory-based partitioning. There were these lock-ins, central lockings on these on the metastore, and there's also issues of tight coupling between the file system and the HDFS and MapReduce. So they needed to evolve that system from something else. So then came the Iceberg. There were many other engines that came in, but Iceberg specifically solves it at the specification layer, as I put it there. So it's not like a wraparound around Hive. It's completely different model. And then for how a table is defined, how it's discovered, how it's versioned, all these things are different from Hive. And that's what makes it truly multi-engine accessible. It's going to make it easy for all of those engines to access data from the same table. So because this talk is about Iceberg, I want to give a high-level overview of how Iceberg actually works. There is this is going to be a mental model. It's not like an architectural diagram. I put together something really brief. The three-layer model, where the engine at the top it can be any engine that's mentioned there: the Spark, Trino, Impala, Hive, and then the second layer is the Iceberg format. Where there's catalog, metadata file, snapshot, which I will get into. And then the third layer is your storage. So it's basically like your Iceberg is your contract between the storage and the engine. Because Iceberg is a specification and not a library, it will implement, if an engine can implement Iceberg specification correctly, you basically will be able to read and write from the same table. And that's the entire design goal of introducing Iceberg. And then there are many other capabilities, as you see on the screen: ACID, Hive. Some of the limitations of some other equally capable platforms was that they could not do ACID. Iceberg can do ACID. It can do some hidden partitioning, time travel. So you can go back in time and point in time and redo or fetch all the data from that point. You can do in-place schema evaluation with Iceberg. And row-level deletes, they're actually worth calling out because they'll enable you truly the CDC and GDPR compliance without you having to sort of rewrite the entire partitions. There's incremental reads. All of these are well-known capabilities, but the row-level deletes will actually help you not rewrite the entire thing. So the next slide I put together is about the metadata chain. That's really the heart of this session, where this metadata chain makes things possible. I want to walk you through from top to bottom. Catalog, it stores the catalog is basically the heart of this. It will store the pointer to the current metadata.json file, which is basically a source of truth for Iceberg. And then the next layer is the metadata.json file, which contains the schema, other specifications, and sometimes metadata manifest list. Snapshot is basically really a snapshot, which is an immutable record of data or a table at that state or point in time. And then the manifest list will list all the lightweight summaries of all the existing manifest files. And so that because these already exist, the engines can actually prune without having to read the data themselves. They'll just read the manifest file. One thing I wanted to mention is the concurrency piece. When there are multiple writers writing to the table, right? Iceberg, one of the good features of it is that the writers never have to lock the table. They write their data files and then attempt to. What happens is the write will automatically happen in parallel, and the atomic update for that catalog happens at the end. Catalog pointer, the pointer that I mentioned. So if there are two writers that are conflicting, and then one retries, if there is a situation like that, if one writer is retrying, so what happens is that towards the end, there will be an optimistic locking, like an optimistic lock-in database. You will have an atomic update at the end. And there's also time travel. It's an extremely powerful feature for ML teams because they need reproducible training data set without copying data. So in this case with Iceberg, you don't have to copy, but you could just time travel to that point and grab the data from there. So the right path for writing data in Iceberg table is sort of sophisticated than we might expect. A lot of steps are involved. First thing is you would write the data from the file to the table location, which is usually backed by an object store. And then in this case, as I mentioned, no logs are required, or there won't be any logs. You can continuously write. And then there's a manifest file. Manifest files are basically every time there is a snapshot, a new manifest file will be created. A manifest list will have all the manifests for those snapshots. And then you create a new metadata JSON every time a new snapshot happens. So the step 5 is sort of critical because the atomic catalog commit, that's what it reads, where before this step, everything is writing files to the object store, which is kind of easy, cheap, and you can parallelize it. The only coordination happens in this step, which is at this point, the single atomic pointer will swap with the old metadata file. When the new snapshot happens, the swap of the pointers happen. So this design has two major benefits, which is the writers can proceed to write in parallel. There's no locking or any overhead until the commit phase comes. And if the commit fails, for example, at the end, due to some form of concurrent writer conflict, only the final step will be retried, and the data will need not be rewritten. The writing files will still be fine. The commit phase, the writer will retry to commit. For example, when streaming workloads in Flink, you can have like dozens of tasks writing in parallel and then coordinating safely through this kind of feature in cataloging. You can achieve that with Flink, and Hive or some other Impala, other engine can read off of this shared catalog, tables in the shared catalog. One more thing is the engines that we saw in the first slide, on the Iceberg slide, we need to select the engines that are specifically designed to help a specific use case. All these engines are not necessarily competing, they're sort of complementary. Like a good architecture will have all three, but just that pick which is best at what. For example, Spark will own the heavy lifting of transforming lots of data, training a model, or running if you have a multi-join aggregation or something like that, you could use Spark. That's the right tool for it. It's not necessarily for fast queries or interactive queries. That's for Trino is for speed. Trino, you have like sub-second, few seconds of SQL queries. You could, this is for your BI tools. You should hit like if you want something really fast, you could use Trino. And Flink, for example, is also for real time. Like right now, if you need something, the data should be fresh from Kafka to Iceberg with exactly one's guarantees or whatnot. So Flink can be your answer. So what I'm trying to tell is, it's the beauty of Iceberg is that in this case, Flink can write the data, and Spark can run the ETL, and Trino can serve it to the BI, all from the same table with no copies involved. Really, the catalog is the glue that holds all these engines together. It's like what it's doing, it's really simple. It is mapping the table name to the metadata file. The whole point is that this coordination is so lightweight, and it will contract with any engine that you put on when you implement it. And there's a Cloudera, for example, has REST catalog for Iceberg, where it standardizes an API for some languages, and then you can call that, and it will decouple the catalog logic from the engine-specific implementation, and then you could use that for multiple use cases. Hive metadata catalog is sort of the migration path for existing Hive tables. I put it there because I've seen a lot of people using Iceberg have Impala Hive tables, and you can run for those Hive workloads, you can run Iceberg tables side by side with Hive tables in the same metastore, and then this is what Cloudera does out of the box. They'll help you with the migration. It's also documented extensively, but that's an approach people take from migrating from Hive workloads to Iceberg. There's also something called as Nessie. It adds like these Git-like branching to your catalog. You can create a branch and then run ETL jobs on it, validate results, and merge all those at the end. It's useful if you're testing schemas changes for ETL without impacting production, something like that. If you notice, there's Hive and Impala in the catalog, so Cloudera actually supports it out of the box for their Iceberg integration directly. So schema evolution is one of the Iceberg's most somewhat underrated features in day-to-day operations, right? When you look at Hive in the past, one of the classic problems of Hive is when you add a column, it requires an alter table, and that changes the schema globally. But the existing files don't have that column, which will lead to query errors or nulls in some of the places that you don't want that to happen. So renaming a column will break the downstream query that references to the old name. In Iceberg, what happens is Iceberg actually solves this problem with column IDs. Every column gets a integer ID at the creation itself. So when you rename a column, only the display name changes. The ID will stay the same, and it's kind of practical, and regardless of the current schema it calls, it will still have that ID intact, and it'll always resolve to that column. You might want to test the schema changes against all the engines before committing to the production. When Spark can gracefully handle some of the older version issues of Impala, but sometimes it will throw errors when they're typing errors. So we might want to block all those things before, test the schema changes before going to production. I wanted to spend a little bit of time on Cloudera's approach. They came up with something called as this open data lakehouse. They're kind of enabling data-driven analytics with combining their warehouse features and data lake features. So you have unified access to all semi-structured, structured, and all kinds of data that you throw in the data lake. And then they already have integrated SQL engines like Impala Hive, so you could actually build analytics using the same data and tools. Simultaneously, they've introduced ML and AI inferences. With NVIDIA, they have a partnership. Visualization layer was also newly introduced. And then there's governance, which is the crucial piece, that their USP. So yeah, if you're looking for supported Iceberg offering, then with multiple engine support, you could go for Cloudera's offering because they sort of do it with governance in place. You could trust their years of experience in warehousing. So yeah, I just wanted to tell you that this lakehouse concept was adopted by Databricks and other companies. They all, on Snowflake, they all work on the same fundamental theory that you're combining capabilities of warehouse and data lake, and you're creating a data lakehouse. Coming to Cloudera specific features, they're also overlapping with the ones that you saw previously, almost the same ones. But what sort of these people have, like Cloudera has, is like they have a hybrid cloud capability. They also can do integration with Ranger, and if you have Ranger in place, they could do that. One more thing that stands out in Cloudera's offering of Iceberg is that they have in-place table evaluation, so allowing the schema changes such as adding, renaming, or other kind of column changes without having to rewrite the underlying data. So the teams can basically adapt to changing business requirements quickly, maintaining the data access seamlessly. The rest of the time travel, snapshotting, table maintenance, these are all very much in sync with the open source Iceberg capabilities. They have something called as Lakehouse Optimizer. It's not open sourced, but it's like an automated service that will continuously optimize the Iceberg tables to improve the cost and performance trade-offs. So they have some benchmarks published, but they say that Cloudera says that they have achieved like 40 to 80% storage cost reduction and somewhat of a 2 to 4x query performance. So if you are interested, maybe check them out. Yeah, I just wanted to put another slide on how the Cloudera is actually at the core. They're optimizing they put in their optimizer to make sure that the performance and cost are intact, and they have a REST catalog, as I mentioned, that enables multiple engines to access the governed data from the same table. It's kind of secure in a way because they have many years of experience in building Ranger and other policy-based things. So if you have existing Hive tables, moving to Iceberg, if you're planning to, in Cloudera, open source or even managed, you could take some steps. I listed a few. I'll share this document later. Maybe you can look at those. On a high level, some of the important caveats is that you need to make sure that the Hive tables are external, not managed, so that because the managed ones will take a different path. Hive will own the files, so you want to make them external files first. There are steps for compaction, meaning Hive generally does so many tiny files, so Iceberg will not do well with these smaller files, so it will struggle with the planning and performance. So there's compaction that's required. And then and Cloudera will usually test with all the engines before declaring any migration is complete. So yeah, sometimes there can be issues across engines, right? So they'll check before the migration. And other details I added, like how alter table, other things like technical details are also there. Some of the operational best practices I've seen with Iceberg are many, but I only listed 6 of them. First one being the file size. Some teams neglect this. 128 MB is a good starting point, is a starting range for Parquet file. But the exact sweet spot but that will depend on your query pattern. The smaller files are better for heavy write situations, but for larger streaming workloads, for larger files, analytic workloads, scans will be easier. So it just depends on what the use case is. You might want to measure appropriately and then size the files. And we need to put in place a compaction cadence so that your write frequency will match with the tables that are being written to. The Flink jobs, for example, Flink streaming tables, they might need a compaction hourly, whereas daily batch tables need it. They won't need hourly, but they'll need a weekly compaction. So you might want to put in a cadence based on what type of table it is. Next is a snapshot expiration. It's kind of a housekeeping task you have to do because the metadata files from 6 months to 1 year will coagulate and it'll become a significant planning overhead at the query time. So you might want to expire some snapshots. There's also orphan files that you want to clean up. It's very important to clean up the files, and the Flink, for example, sometimes will crash midway if there's too many orphan files. So yeah, you might want to initiate cleanup of those files before your storage bill will go high. So some of the things, I think this is specific to Cloudera. So if you have Impala in place, Impala vectorization is something you can do. It's worth your time if you really have if you have Impala workloads. Cloudera has published benchmarks that will show Iceberg with Impala's native vectorized Parquet reader. It performs 10 times faster than Hive external tables for the same queries. So you might want to check out for larger scale workloads, you can implement Impala vectorization instead of Hive external tables. And then the compute stats point is you might want to look at the computation stats before migrating Hive tables to Iceberg, because this compute, I don't know, I think I can skip this because this is specific to Impala and Cloudera migrations. You might not know about this, but if you know, running these compute stats it's sort of a trap. You might want to avoid that. And then for very large tables, you want to use another command which is compute incremental stats. I actually have this only for Impala. Yeah, that's this slide is specifically for. I'll share the slide deck, so you might, if you find it useful, you can use it if you have Cloudera distribution. I wanted to also list some of the common pitfalls in real production incidents that I've seen with Iceberg deployments. First thing is you do not want small files. After migrations, the number one performance issue I saw is that post-launch, there are small files and they don't realize it because Hive era made it very typical. You might want to avoid that by creating automated compaction. And also catalog misconfiguration issues is very common than it should be. So you might, if you have Spark, Glue, Trino that are using HMS, they will write to previously will write to separate catalogs, right? In this case, data is invisible across engines, so that will make the debugging hard. So we want to make sure that all these engines are writing to the same catalog instance. That way you can easily debug. Previously, it will write to different HMS catalogs. So because of those separate catalogs, it's hard to debug. For Cloudera specific workloads, you might want to check with the release notes. They have a lot of version mismatches and Iceberg features that are available in Hive and Impala. The parity between the engines will kind of lag behind the open source Spark implementation sometimes. For Cloudera, that's a big issue. If you've used Hive, this is only for Cloudera. So the takeaways I have from this session, my knowledge is that Iceberg is not necessarily just like a technology upgrade. It has to be an architectural shift. So it has to be a decision that involves thinking: do I need decoupling between my analytics layer and storage layer? Does that even make sense? What does that enable our teams to do? Think about that, and if there is a shift that is really required, then Iceberg was it will help you in many ways. And then the engine selection, as I mentioned, it's a design also, not just a preference. So you have to make sure that the engine for that workload is not just it shouldn't be harmful for other engines, or it shouldn't take away all the resources, things of that nature. So when analysts are running Spark, interactively, engineers are using Trino for bulk loads or whatnot. So there are somewhat of anti-patterns you might want to look at from a design approach and pick your engines carefully. And metadata it will define your performance story. So you have to be careful on how well partitioned and compacted iceberg tables are. That way you will avoid the small file situation. Sometimes a compacted iceberg table, which is on a smaller cluster, will outperform a larger cluster and also poorly organized table. So it's important to plan accordingly. Yeah, operations are kind of a daily job to keep the lights on. So make sure that operations are not optional for iceberg tables. And if you're using Cloudera already, they have a governance layer which will take care of the maintenance. They have a built-in security and lineage on top. So yeah, check this out. And that's all I had. And thank you so much for your attention and time. I will. You can connect with me on LinkedIn and ask any questions if you have. Thank you.